Welcome to the Student Academic Learning Services Introduction to Stoichiometry video. This video is designed to reinforce the purpose and use for stoichiometry, introduce you to a method for solving stoichiometric problems, and then we'll do an example together. Let's get started. Stoichiometry, though it sounds like such a big, scary word, is essentially just the study or calculation of the relationship between different molecules in a reaction. The purpose for using stoichiometry is to calculate things like the amount of products that can be produced with a given amount of reactants, or also to find the percent yield. It's used in the real world by scientists who may want to know how to obtain a specific amount of a chemical, or a good analogy is in cooking or baking. Say you want to make a specific recipe like Grandma's chocolate chip cookies, but you only have a limited amount of sugar in the cupboard. So you'll have to figure out how much of all the other ingredients you need based on your limited supply of sugar. This is essentially what we're doing in stoichiometry. We're using ratios from balanced chemical equations to determine quantities of the other reaction participants. Here's just a reminder of some of the things you need to have and understand before attempting to solve stoichiometric problems. First and foremost, you need a balanced chemical equation. If, in your problem, you're given an unbalanced equation, then you will need to use a method to balance it before you proceed. For assistance with balancing chemical reactions, please see the videos supplied on the Student Academic Learning Services website. Secondly, you will need a mole ratio at some point or another in your conversions. So depending on which two reaction participants your problem identifies, a mole ratio can be set up by using stoichiometric coefficients. For example, in the reaction shown here of hydrogen and oxygen gas to produce water, a mole ratio between hydrogen gas and water would be written as 2 moles of hydrogen gas for every 2 moles of water, or 2 moles of hydrogen gas over 2 moles of water. This essentially says in literal terms that for every 2 moles of hydrogen gas reacted, 2 moles of water will be produced. Another important aspect to remind you of is that you will also need to be using molar masses, also known as molecular weights, in your conversions. Do you remember where you can find those if they aren't given to you in your problem? If you said periodic table, you're right. Remember where to locate your molar masses. They're indicated as the atomic mass on any given periodic table. There are still a few more things you need to know, but rather than speak about them all separately, I'm going to provide a diagram that brings everything together for your conversions. As you can see in this diagram, we have the mole as our central common unit. That's because no matter which units you need to convert between, you will always need to get your moles first. From there, you could do any of the following things. You could use the stoichiometric mole ratio from your balanced chemical equation to jump to another reaction participant. You could use the molar mass to determine your actual mass of the reaction participant of interest. That would be using this conversion right here. So that's where the need of your molar mass will come in. You could use Avogadro's law, stating that at STP, which is standard temperature and pressure, the volume occupied by 1 mole of any gas is 22.4 liters. You could use this to find the actual volume of any given gaseous reaction participant. And here's the conversion for that. Or finally, you could use Avogadro's constant, which is 6.02 times 10 to the 23, to determine the exact number of particles, molecules, or atoms of any given reaction participant. And the conversion for that is right here. Now that we have reviewed the background information necessary for stoichiometric problem solving, I'm going to introduce a method to you. Having a step-by-step approach should make it easier to attempt a stoichiometric problem, regardless of the level of complexity. So the steps are: number 1, start with a balanced chemical equation. I can't stress enough how important this step is. If your chemical equation is not given to you in a balanced state, you must do this first. If not, your mole ratios between reaction participants will be wrong, and no matter what, your final answers will also be incorrect. So number 2, convert the given information into moles. Whether the question provides you with the mass, a number of particles, molecules, or atoms, or a volume, you must convert this given information into a number of moles. Number 3, now calculate the number of moles of the required substance, and you will do this using a mole ratio. You obtain this mole ratio, of course, from your balanced chemical equation. And finally, number 4, convert that number of moles of the required substance into either a mass, a number of particles, molecules, or atoms, or into a volume. This will also depend on what the question is asking for. You may find this diagram of the problem-solving process helpful. Basically, in any given stoichiometric problem, you'll be converting from a given substance to the required substance. And one of the skills you need to gain is being able to determine which is which in your problem. So we will work on this. And also, depending on what data is provided to you in the problem, will determine how many steps you'll need to take to get to your answer. In this diagram, the first 2 boxes, if you begin from the left, are the possible starting points for you in any given problem, and the 3rd and 4th box represent the possible endpoints. Each arrow in between represents a step, and the information needed to perform each step is indicated above the arrows. For example, if you are given the actual number of moles of one substance from your balanced chemical equation, and you're asked to convert that to the actual number of moles of another substance in the reaction, using that data, you will only need to take one step, shown here. And you'll actually be using your mole ratio from your balanced chemical equation to make that one step. There are 2 other possibilities, which we will come across in our practice. There's a 2-step and a 3-step process, but for now, let's move on to a simple example problem. Here's our first example problem, and notice that I've copied the method in the upper right corner for us to refer to. The problem asks how many moles of oxygen gas are needed to produce 3.7 moles of nitrogen monoxide. And the very first step that you should always take is to check and make sure that the chemical equation you're given is balanced. Let's check this one. On the left, there are 2 atoms of nitrogen as well as 2 atoms of oxygen because of the subscripts. On the right, however, there's only 1 atom of nitrogen and 1 atom of oxygen. So that means that our current chemical equation is not balanced. And we can easily balance this by doubling. So we need to double the atoms on the right, and we can do that by adding a coefficient of 2 in front of our nitrogen monoxide. So now, take a look over it again, and you'll notice that our equation is now balanced. In the next step, you have to make a decision. If necessary, convert the given information into moles. Well, in our problem, the data provided is 3.75 moles of nitrogen monoxide. So in our case, we do not need to make this conversion. We're already given the data in moles. We do need to realize, however, and you can even mark this down if it helps, which substance in our reaction is the given substance and which one is the required. Well, we've already kind of mentioned that we're given data for nitrogen monoxide, so that would make nitrogen monoxide the given substance. So I'm actually going to write that down right underneath nitrogen monoxide on the reaction. So it's the given. And if we read our question again, it's asking how many moles of oxygen gas are needed. So that would make oxygen gas in our equation the required. And I'm going to mark that down as a question mark underneath oxygen gas on the equation. So now you've identified your given and required substances. This has prepared you well for step 3, which is to calculate the moles of the required substance using a mole ratio. So let's go ahead and find our mole ratio now. In order to be sure that you always set up your mole ratio correctly, here's a formula to remember. The mole ratio should be written as a fraction so that we can multiply our data against it easily. The mole ratio fraction will always be set up as the moles of the required substance over the moles of the given substance. And these numbers will come directly from the coefficient in your balanced chemical equation. For ours, the mole ratio will end up being 1 mole of oxygen gas, because there's only 1 mole of it in our balanced chemical equation, over 2 moles of nitrogen monoxide because of the coefficient 2 in our balanced chemical equation. So now that we have this fraction, we can multiply our data, which is 3.75 moles of nitrogen monoxide. We can multiply it against this mole ratio. Remember the rules of cancellation in mathematics? Well, that's going to apply here. So we can cancel out moles of nitrogen monoxide on the bottom of the fraction, as well as the moles of nitrogen monoxide in this piece of information. So when we actually calculate it, because we've canceled out those units, and the calculation is actually 3.75 divided by 2, so our new number is 1.875 moles, and it ends up being moles of oxygen gas because of these rules of cancellation. And just to double check here, isn't this what the question was asking? It was asking us how many moles of oxygen gas are needed. So now we know, because of this calculation, that we would need 1.87 moles of oxygen gas to produce 3.75 moles of nitrogen monoxide. So well done, everybody. To finish off, I want to point out to you that because our question was asking for the moles of oxygen gas, we actually do not need to complete step 4 because it's not necessary to convert these moles of the required substance into mass, particles, or volume. The question wasn't asking for that. So if that is the case in your question, then you can just be finished at step 3. And the next thing I'm going to do is just do a quick summary of what we did to get to our final answer, so that hopefully you can apply this strategy to some similar questions and practice with those before you move on to more difficult ones. The first thing we did was made sure that we had a balanced chemical equation. Sometimes in your problem, your equation will be given to you in a balanced form, but sometimes it won't, so you always have to check that. And in our case, we ended up having to balance our equation. It's necessary to do so. The second thing we did was check to see if our given information needed to be converted into moles. But in our case, it didn't, because the problem gave us the data in moles already. But you definitely need to check that before you proceed. Next, we calculated the moles of our required substance, which we determined was oxygen gas, remember? And we did this by setting up a proper mole ratio. Now you know the formula for a mole ratio, and you can apply it to any question. Finally, we determined that we did not need to move on to step 4, because our question was asking for an answer in moles, and we calculated that in step 3. If you recall the diagram introduced to you earlier, we have just solved the problem in which we were converting from the moles of a given substance to the moles of the required substance. This is also known as a one-step problem. For a guided explanation on solving 2-step and 3-step stoichiometric problems, please visit the Student Academic Learning Services website. This concludes our video on the Introduction to Stoichiometry. If you have any questions about the content covered in this video, please visit the SAL Center, which is located in room 204 of the Student Services Building, and make an appointment with the appropriate Learning Skills Advisor. Thank you for watching.